for an equilibrium reaction involving gases, the forward reaction is first order while the reverse reaction is second order. Then the units of Kp for the equilibrium is asked. Now you see, if you take any particular reaction where A moles of A is reacting with B to produce C and D, we know that the units of K, I mean to say equilibrium constant if it is expressed in terms of the partial pressure, are atmosphere whole power delta n. And we also know that the equilibrium constant is the ratio of the forward and backward rate constant. I mean to say it is equal to Kf upon Kb. Now it is given that the forward reaction is first order while that of the backward is second order. That means here the units of this concerned reaction, when you write in terms of the atmosphere, will be atm whole power delta n, that is equal to 2 minus 1, or atmosphere whole power 1. So the answer for this question should be option A, that is atmosphere whole power 1. It all depends upon the sign of this delta n, and delta n is nothing but the order of the reaction for the backward minus order of the reaction for the forward. We have 1 mole of N2O4 gas at 300 Kelvin is kept in a closed container under 1 atmosphere. It is heated to 600 Kelvin when 20% by mass of N2O4 gas has decomposed to NO2. Now the resultant pressure is asked. Now we know that N2O4, which is in gas phase, is dissociating to produce NO2 gas, is present at equilibrium at 600 Kelvin, but you are provided with the initial moles of N2O4 as 1, this at 300 Kelvin only. So therefore, now when I consider this equilibrium to be taking place at 600 Kelvin, because you have been given that at 600 Kelvin only it is dissociating completely to produce 20% by mass of this NO2 gas. Now when I consider the equilibrium, suppose some x moles of N2O4 have dissociated, which are present at 300 Kelvin. For every 1 mole you are getting 2 moles of NO2. Hence for every x mole dissociation of NO2, we can anticipate the 2x mole of NO2 be produced. But these are the number of moles of what you call the substances at what you call 300 Kelvin. Now we need to find out the number of moles at 600 Kelvin. For that we will use the ideal gas equation. Now we know that as per ideal gas equation, when we substitute PV is equal to nRT and the given data, pressure initially taken to be 1 atm and it's a closed vessel, volume remains constant, and initial number of moles of N2O4 are taken as 1 into R into temperature initially is 300 Kelvin. Now we have heated this equilibrium mixture to 600 Kelvin, where the total pressure we need to find out or obtain is taken as P. The total volume of the vessel is, once again, it's a closed volume, so therefore V constant, and number of moles, the total moles at equilibrium are 1 minus x plus 2x into R into 600. So therefore when I divide these two expressions, we have volume getting cancelled, P is equal to 1 plus x into 2. So this simplification of this equation will give you the relationship between pressure and the number of moles of N2O4 dissociated. Now one more information is provided to you in the question, that 20% by mass of N2O4 has undergone dissociation. That I am going to use. Now the number of moles of N2O4 dissociated are x. So therefore mass of this N2O4 dissociated, because it is given that weight of N2O4 dissociated divided by total weight, that is weight of N2O4 and weight of NO2 into 100 is provided to us as 20. Now it is given that the moles of N2O4 dissociated are x, moles into the molecular weight of N2O4 will give you the weight of it, divided by once again moles into this thing dissociated plus the weight of NO2, that is So this simplification of this expression will give you the value of x, and that x upon substitution here will fetch you the total pressure. Now you can see here that when we have written this as the weight of N2O4 and weight of NO2, we need to take this as the remaining weight, because the total weight that is remaining in the equilibrium mixture for N2O4 is 1 minus x. Now simplification of this expression will give you the x, which upon substitution here will give you the value of P, and answer for this question is 2.4 atmosphere, that is option A. Now for this reaction we have x moles of A giving rise to 1 mole of C and 1 mole of D. Let us assume that the initial concentration of this A to be some A, and at equilibrium suppose alpha moles are dissociated, then degree of dissociation is alpha, then the remaining concentration of A is A into 1 minus alpha, and the moles of C and D are obtained to be A alpha upon x and A alpha upon x as well, because you can see for every x mole 1 mole of C is produced, for every A alpha by x will be produced. Now when I write the equilibrium constant Kp, you can see A alpha by x into A alpha by x, that is whole square, divided by A into 1 minus alpha whole to the power x. Now you want this expression to be completely independent of the term A, initial concentration, then for that you know the x need to be taken as 2, because when I take x to be 2, it will become A alpha by 2 whole square divided by A into 1 minus alpha whole square. This A term gets cancelled completely, and your alpha will be dependent only upon the Kp. So therefore the substitution of the 2 in place of x will fetch the equation wherein the alpha is completely independent of the initial concentration. So therefore answer for this question is option C, that is x is equal to 2. At temperature T, a compound AB2 dissociates according to the equation with the degree of dissociation value to be x. If the value of x is too small compared to unity, then you have been asked to find the relationship between Kp x and the total pressure P. Now let me write the concerned equilibrium reaction. 2 moles of AB2, which is a gas, dissociating to give 2 moles of AB gas and B2 gas. Now initial moles you can assume as anything, because you will be writing Kp. So when we are writing Kp, we will be taking the partial pressures. When we take partial pressure, we take the mole fraction. When we take the mole fraction, no matter what you take here, it's going to get cancelled, because initial moles let's assume as A, then final will be A into 1 minus alpha. So when you take the ratio of the two, A gets cancelled. So therefore whatever you take, it's given that the dissociation is to the extent of A. For every 2 moles of AB2, you are getting 2 moles of AB. So therefore for every x moles you can anticipate the x moles formation, whereas for every 2 moles you are getting only 1 mole. For every x you can expect the formation of x by 2 amount of B2. Now when I am writing the expression for Kp here, it will be partial pressure of AB square, that is mole fraction, moles of AB by total moles, into, let's assume that the total pressure of the equilibrium mixture to be P whole square into x by 2 divided by 1 plus x by 2, that is moles of B2 divided by total moles into P divided by the moles of AB2 by total moles into pressure whole square once again. Now when I am simplifying this expression, because you have to get an expression for Kp in terms of x and the total pressure P when the x value is very less compared to 1. You can see here when the x value is very less compared to 1, I can eliminate these terms compared to 1. When I am eliminating these terms compared to 1, because their values are too small, I am getting Kp is equal to, here P square getting cancelled, Kp will be equal to x into x by 2, and here the square of x is remaining. So x square into x by 2 into P upon this, and this got cancelled and P square got cancelled for that. So therefore you are getting Kp as x cube P upon 2. Now the correct answer for this question is option A as per this. We have an equilibrium system, and if the concentration of C at equilibrium is increased in such a manner that at new equilibrium its concentration becomes exactly double, then it will cause the equilibrium concentration of B to change too. I mean to say, where first you need to write the concerned equilibrium reaction in such case. In all such cases, we have to assume that here the temperature has been maintained constant, so therefore the Kp or Kc is not going to change. So now I'll assume that at equilibrium directly the concentration of B is square bracket B and concentration of C is square bracket C, where the value of Kp will be obtained to be B to the power 2, because it's what you call the concentration is taken as concentration square bracket of B and the coefficient is C, and here 3 moles of C is given, so therefore it will become C to the power 3. Now we have disturbed this equilibrium and we have re-achieved the new equilibrium. So at new equilibrium, where temperature is kept constant, unless it is mentioned that temperature is changed, we are not going to change the temperature and the value of Kp remains constant. So Kp will become equal to, I'll assume that the new equilibrium concentration of B to be B prime, because here when we have caused the disturbance in the C, the equilibrium will shift in the backward direction, hence decreasing the concentration of B as well. You can see, my dear students, here I am increasing, I am doubling the concentration of C. So when the concentration of C is doubled, the concentration of B also decreases, because this equilibrium is forced to shift in the backward direction as per Le-Chatelier principle. Now the concentration of C has been made 2 times the concentration of C initially, whole power 3. So therefore it will become B prime square into C cube into 8. Now we know that Kp remains constant throughout. So Kp equal to B square into C cube is unchanged. B prime is the new concentration of C at equilibrium. So when I simplify this, B prime is turning out to be 1 by 2 root 2 times of the initial concentration of B. So therefore in this question the correct answer is option D, where the concentration of B final will be 1 by 2 root 2 times of the initial concentration of substance B. We have a reaction where CaCO3 and CaO are solids. The only substance which is involved in the equilibrium, which is a gas, is CO2. Now when we have added more amount of CaO, the question asked what happens. Now since the equilibrium involves 2 solid components, that is CaCO3 and CaO, here if there is any shift in the equilibrium, that will be only due to the carbon dioxide, because the active mass of pure solid is conventionally taken as 1. Since it has got no role to play in finding out the value of equilibrium constant, we can say here the addition of calcium carbonate, calcium oxide, which happen to be the pure solid, has no effect on the equilibrium. Not only this, any pure solid or liquid when being added, there won't be any effect on the equilibrium, hence there won't be any effect on the concentration of CO2 as well. So correct answer for this question is option C, that has no effect on the equilibrium. Now we have an aqueous solution whose volume is 500 ml and an ionic reaction is taking place where the silver ions are replaced by the copper. It has reached the equilibrium with concentration of Cu plus 2 being x molar. Now when we have added more water at equilibrium, what exactly is the situation the question asked. Now I am writing the concerned equilibrium reaction here, where the active components of this equilibrium are only Ag and Cu. Now this is a mixing case, so therefore we will be converting the concentration terms into number of moles. Now when the moles at equilibrium are obtained in terms of x, you can see the molarity of Cu plus 2 solution is x and volume is 500 ml. So when I multiply the molarity with volume in liter, 500 milliliter means 0.5 x happen to be the number of moles of Cu plus 2. Now it is given at equilibrium what will be the concentration of Cu plus 2 when I have added 500 more ml of water. Now when I am adding water here, that means when volume is increased, as we know that equilibrium shift to that side where the moles are more. Here you can see the product has only 1 mole of the active component, whereas reactant has 2 moles of the active component. When I have increased the volume as per Le Chatelier's principle, this equilibrium is supposed to move in the backward direction. That means when it is moving in the backward direction, for every 0.5 x mole, I am finding out here the mole, 0.5 x mole, suppose some y mole have undergone dissociation, for every 1 mole I will be getting 2 moles of this. So 2y mole of Ag plus will be obtained. Now these are the final equilibrium moles of Cu plus 2 and Ag plus, and the concentration of Cu plus 2 will become number of mole upon volume in liter. Previously it was 500 ml, you have added 500 more ml of water, so therefore 1 liter. So it happened to be that the number of moles of Cu plus 2 or the concentration of Cu plus 2 final would be definitely here less than x by 2. I mean to say the correct option for this question will be option D, where the concentration of Cu plus 2 at new equilibrium is less than x by 2, that is x by 2 minus y. You can see here this value is equal to x by 2 minus y. So the new equilibrium concentration of Cu plus 2 will be less than x by 2. We have the equilibrium of dissociation of SO3. The molar mass at equilibrium was given to be 60. Then the degree of dissociation of SO3 is asked. Now when I take the dissociation of SO3 into consideration into SO2 and O2, we know the relationship between degree of dissociation and vapor density as this, where capital D is initial vapor density. Initial vapor density of this reaction is only due to SO3. Hence we have the SO3 molecular weight as 80 upon 2, which is the capital D given to us. Then the degree of dissociation is asked by giving the equilibrium molar mass. The equilibrium vapor density, this is due to SO3, SO2 and O2. The small d will be equal to molecular weight at equilibrium by 2, which is given as 30 in this case, because the equilibrium molar mass is given as 60 to us. We can find out the value of small d. Now when I substitute in that equation, I have capital D 40 initially due to SO3, molecular weight of SO3 is 80 upon 2 by 30 into N. The number of moles of the products produced from 1 mole of SO3 is 1.5 or 3 by 2 into the small d is again 30. So this is the expression what we have for alpha. That means when we simplify, we are going to get this as 10 upon 15 or 2 upon 3, that is 0.66. So the correct answer for this given question is option B, that is 0.66 or 66% of dissociation have taken place. Now we have the equilibrium reaction. 2 moles of A is reacting with B to produce 3 moles of C and D. 2 mole each of A and B were taken in 1 liter of the flask. Then which of the following must always be true when the system has attained the equilibrium? Now when I am writing the concerned equilibrium reaction where 2A is reacting with 1 mole of B in gas phase to give you 3 moles of C and D. Now we have taken 2 mole of each in equilibrium mixture. The concentration of these two happens to be always 2 and 2 because the volume of the vessel is 1 liter. Now when the equilibrium is reached, suppose some x are the moles or concentration of A underwent the reaction, then the remaining mole of A were found to be 2 minus x. For every 2 mole, you can see 1 mole of B has reacted. For every x, we can anticipate only 2 minus x by 2 to react, x by 2 to react, remaining will be 2 minus x by 2. For every 2 mole, we are getting 3 mole. For every x, 3x by 2 mole of this and x by 2 mole of D to be obtained. Now during the course of the reaction, you can see that 2 minus x by 2 is always less than 2 minus x. So, therefore, the correct answer for this question will be the concentration of A is less than that of concentration of B. Here from this relationship we know that 2 minus x value will be less than 2 minus x by 2. If I substitute the value of x to be 1, it is turning out to be 2 minus 1, whereas if I am substituting here x as 1, the value 2 minus 1 by 2, that is 1.5. So, therefore, this value is obviously less than that of this. So, the correct answer for this question is option B, that is concentration of A is less than that of concentration of B at equilibrium. We have Kp for a reaction at 25 degrees Celsius as 10 atmosphere. The activation energy for the forward and backward reactions are provided to us as 12 and 20 kilojoule respectively. Then the K value is asked at 40 degrees Celsius, but you notice here that the value asked is Kc but not Kp. So, therefore, here for a given equilibrium, when I am drawing it for the activation energies of the forward and backward, you can see this is the activation energy of forward reaction and this is the activation energy of the backward reaction. So, therefore, the difference is nothing but delta H. So, we always calculate the value of delta H by using the difference in the activation energies of forward and backward. In this case, it is given as 12 and 20. Hence, the value of delta H in this case is 12 minus 20 kilojoule per mole. Now, after knowing the value of the delta H, you need to find out the Kp value initially at 40 degrees Celsius. Now, Kp2 at 40 degrees Celsius, you need to find out the Kp1 value. You can see here Kp1 value at 25 degrees Celsius is provided to us, is found to be 10 atmosphere. Now, when I am substituting here, I have already got the activation energy relationship with that delta H, the delta H upon 2.303 R. I am going to substitute it as 18 to 10 to the power minus 3 because this value we have calculated in kilojoule per mole into 1 by initial temperature is 298 Kelvin and final is 313. Obviously, from this we will be finding out the Kp at 40 degree Celsius. Now, the question asked to us is to find the Kc value at 40 degrees Celsius. Now, we know that Kp is equal to Kc into RT whole power delta n. You can see from the units of Kp, we can make out that delta n is given as 1. So, therefore, Kp at 40 degrees Celsius after obtaining from here, after substituting the value here, you will be getting Kc provided you substitute RT as well. Temperature is asked at 3 Kelvin. 313 will be obtaining the value of Kc. So, therefore, after simplification of this, the correct answer for this question is option C, that is 0.33 mole per liter. For the reaction XO with O2 to form XO2, the equilibrium constant is given to us, that is Kc is given to us as 1 into 10 power minus 4 mole per liter. If 1 mole of XO and 2 mole of O2 are placed in 1 liter flask and allowed to come to an equilibrium, at equilibrium the concentration of XO2 is asked. So, when we write the concerned equilibrium reaction, where we will assume that all are being the gases. Now, it is given that 1 mole of XO and 2 mole of O2 are taken in 1 liter flask. So, when the equilibrium is achieved, suppose some x moles have dissociated from 1, then the remaining mole to be 1 minus x. For every x by 2 mole will react here, the remaining mole will be 2 minus x by 2. For every 1 you are getting 1 mole, hence x mole of this thing is obtained. Now, these are the equilibrium concentration because the volume of vessel is given as 1 liter. Now, the Kc for this equilibrium is 1 into 10 to the power minus 4, which is equal to the concentration of XO2, that is x upon concentration of XO into concentration of O2 whole power 1 by 2. Now simplification of this will fetch you the concentration of XO2 at equilibrium, because here in such cases you can see that the value of equilibrium constant was found to be very low. So, you can neglect the values like x as well as the x by 2 when compared to 2, and after simplification the value of x will be obtained to be 1.4 into 10 to the power minus 2 mole per liter. Hence, the correct answer for this given question is option A. We have 10 gram of solid calcium carbonate is taken in a vessel of 1 liter volume at 1000 Kelvin. When CaCO3 decomposes to give CaO and carbon dioxide, and if Kp for the dissociation of CaCO3 is given, the pressure of CO2 in the vessel is observed to be how much is being asked. So, when you have taken CaCO3 and when it reaches the equilibrium, we have no ambiguity in writing the Kp for this equilibrium as partial pressure of CO2, since it is mentioned that this reaction has reached equilibrium in that particular vessel and Kp value happened to be the partial pressure of CO2. So, therefore, correct answer for this question is option C. We have the equilibrium in a closed vessel where N2O4 dissociating to produce NO2. At a constant temperature, if the volume of the reaction vessel is halved, then which of the following changes might take place? Now, since we have this equilibrium with us, you know, as long as the temperature is constant, the equilibrium constant also remain constant, but the volume of vessel is halved. When the volume of the vessel, I mean to say when volume of the vessel is decreased, halved or whatever, then equilibrium shifts in backward direction here in this case, because when volume is decreased, the corresponding number of moles also will decrease. I mean to say the equilibrium will shift to that direction where the gaseous moles of the substances happen to be less. So, here the moles of the gaseous reactants are lesser. So, therefore, this equilibrium will shift in the backward direction. So, when I am writing the equilibrium in terms of the degree of dissociation, for every alpha mole dissociated for N2O4 you will be getting 2 alpha moles. So, when the equilibrium is shifting in the backward direction, alpha is supposed to decrease because we are shifting this in the backward direction. So, therefore, correct answer for this question is option D, where Kp do not change but alpha decreases because this equilibrium is shifting backwards. The vapor density of PCl5 is 104.16, but when heated to 230 degrees Celsius, its vapor density is reduced to 62. The degree of dissociation of PCl5 at this temperature is asked. Now, we have solved one similar question where the vapor density values can be used to obtain the degree of dissociation by using the expression. So, where D is the initial vapor density of the PCl5, because only PCl5 is present initially, small d is the equilibrium vapor density. I mean to say when 3 components are present, N is the number of moles of the products formed from 1 mole of the substance. So, it is given to you in the question that the initial vapor density 104.16 is nothing but the molecular weight of PCl5 upon 2 minus the equilibrium vapor density is 62 divided by the N value, the number of moles of the gaseous products obtained from 1 mole of the gaseous reactant are 2. Now, simplification of this equation will fetch us the value of alpha as 0.68, that is option B, 68%. Now, which of the following statement is wrong about the equilibrium state? Various options are given to you. In that, we know that for the equilibrium state, option A indicate delta G is equal to 0. That means the heat of formation of the products when become equal to the heat of formation of reactants, we call it as the equilibrium situation. So, therefore, delta G of a reaction you write the delta G of reaction happens to be delta G of product minus delta G of reactant is equal to 0, and delta G is equal to delta G naught plus RT ln Q, where at equilibrium we can replace the Q with K, and we will be finding out the delta G naught as minus RT ln K. So this relationship is obtained after assuming that delta Eg is equal to 0 for the reaction. That means the rate with which the forward is taking place is the rate with which the backward is also taking place. Hence the option B seems to be the incorrect, because the reaction is being told that it ceases at equilibrium but doesn't cease the rate of forward. The forward and backward are moving, but the rate with which the forward reaction is moving is the same with the backward also moves. So therefore it's absolutely wrong to say that the reaction ceases. Reaction doesn't cease, it keeps moving with the same rate in the forward and backward direction. Now when it comes to the option C, equilibrium constant is dependent on the temperature. It's a very versatile relationship where K is dependent on delta G naught is dependent on temperature, hence K is dependent on temperature, and we have seen that this is the equation which is being used to find the relationship between K and T. Now when temperature is increased, the ratio of the equilibrium constant, this is the equilibrium constant in temperature T1, low temperature, this is the equilibrium constant at temperature T2, high temperature. Now when I have increased the temperature, the ratio of these two depend upon the sign of delta H. If it is an endothermic reaction, the overall value is positive, then K2 will be greater than K1. If it is an exothermic reaction, this overall value is negative, then K2 will be less than K1. So therefore we can say that for the endothermic reaction, equilibrium constant increases with increase of temperature, whereas for the exothermic reaction the equilibrium constant decreases with temperature. And the option D seems to be correct, because catalyst is going to have the equal impact on the forward and backward reaction. So when you have added the catalyst, you can see that this is one path of a reaction which is being decreased equally for the forward and backward by the concerned catalyst. So therefore the presence of catalyst just lowers the activation energy of the forward as well as the backward equally when compared to the previous one. So therefore option D is the correct statement. Hence the wrong statement for the given question is option B. A solubility of a salt in a given solvent, say H2O, is independent of temperature, is dependent on temperature as given by the expression S is equal to some constant A into E power minus delta H upon RT. It is something like the equilibrium constant depending upon the sign of delta H, where delta H is the enthalpy of the solution. That means the heat released or gained when a particular solute is dissolved in a given amount of solvent. Then this solute, when dissolved in water, as we all know that it could be exothermic as well as endothermic. That means heat may be released or gained. For a given solution, the variation of the slope for the graph between log S and temperature is shown graphically. You can see here log S versus 1 by T. They have shown it as the positive slope. So therefore the question asked is to find the solute accordingly so that the slope of the equation is positive. Now we have got this expression, and when I apply logarithm on it, log S will be equal to log A minus delta H upon 2.303 R into 1 by T. Now when I am comparing this with y equal to minus mx plus c, that is slope to be negative with a positive intercept, the slope is comparable. The x coordinate is 1 by T and y coordinate is logarithm of x. Now for the given expression, if delta H is positive, that means when I am dissolving any particular solute and heat is absorbed, then in that case slope is negative. If delta H is negative, if I substitute delta H negative value here, this overall term appears to be the positive. So even for a given question that the slope value happened to be positive because theta is a positive angle, hence we need to see among the options what is that salt which is releasing the heat upon what you call the dissolution in water. We know that the already hydrated and the salt that do not form hydrate do not form hydrate. When dissolved in water, heat will be absorbed. So option A, we have copper sulfate dot 5H2O. It is going to absorb heat because it is already hydrated. And we know that option B, NaCl, it cannot form hydrate, hence it is an endothermic salt. So slope will be negative for it. And third one is sucrose. Sucrose is also an endothermic salt. It comes to CaO. You know, the dissolution of CaO, Na2CO3, Na2S2O3, sodium sulfate happen to be exothermic in nature because they are going to form a strong bond with water, whether it is hydrated or hydroxides. So the correct option for the given question is option D, that is CaO.